welcome. Tonight, general business, not too much going on, but a little bit. And then Father Chris Corbally, our speaker. Sorry, it's taken us a while to get going, but we should have a fun meeting. All right, James Yoder is our property director. Marty is our webmaster newsletter editor. He's not here. His wife had surgery this week, and hopefully things are going well there. Still looking for an events coordinator. We're kind of taming down on events. We're doing a STEM session at the EVAC game on Sunday. I think that's the last event we have scheduled for a while, but we are still kind of working on that. Join or renew your membership. Brooks is in the back, ready to help that. I see we have a couple of new members tonight already. Also, he has stinking badges, a big pile of stinking badges that you do need. So we have badge pickup, and he has a lot of those. So if you've ordered a badge, or you would like to steal someone's identity and wear their badge, that's a possibility also. Observatory, we're open for public viewing Friday and Saturday. We always need volunteers, so if you want to, come see me. Astronomy Day is next Saturday. Go celebrate in your own fashion. But we're doing solar viewing on Saturday, 29th, 9 to 2. So if you're going to come by and stare at the sun, which has been really active recently. So really good stuff to look at. The Messier Marathon took place last month. After a weird weather delay. It was a little windy. It was a little, not super well attended, but everybody was there, had a wonderful time. We had a lot of fun. And James Yoder, our property manager, has some fun things to tell you about, which would be by pressing down to Rob's. We'll get you there.
Okay. How are we doing on time? Because I can do compressed.
Take as much or as little here.
Okay. So James Yoder, property manager, we started, as we've discussed in earlier meetings.
Stay next to the mic.
We started a rental program. And so now we've got 2 telescopes now that we are putting up for rent. This is for members of the club. We got one up here in the front, which is the purple monster there. That's a 10-inch Dobsonian. It's $25 for the first week and $20 per week thereafter, up to 4 weeks. And we've got 2 telescopes, the Dobsonian over here. And then we've got a Celestron Nexstar C8 telescope, and that was built basically on donations from various people in the valley here. So that currently is out to rent. But if you're interested in renting either one of these guys, if you're a club member, just contact me. We'll show you on the page where you can get access to that and find out more information about it. And here's where you'll land at if you go to the East Valley Astronomy Club website. There's a screen. Let's see. I don't know if I want to try to share that or not, because I'm not sure where it's at. But anyway, if you go to the East Valley Astronomy Club website, scroll down. There's going to be a banner there that says something about rentals and equipment for sale. We're also introducing the equipment for sale at this point. And if you click on that, that's going to take you to this website here. And you can click either the sell or rent items, and the sell guy will take you to this. This is our current equipment that we're starting to put out for sale. This is pickup only. If you're interested in buying any equipment, come take a look at here. The manuals and information on all this stuff is here. So I guess that's that. And then there's another rent one that if you go there, you'll find out a lot of information about the rental stuff. So in the interest of the main speaker, I'll take questions real quick and then we'll go through there. Any questions? Okay, sounds good.
Thanks, James. A lot of hard work on that and getting everything to get together. There will be a link on the bottom of the homepage that will take you to this page that you see on the bottom. It's not quite set up yet, but in the next day or two, that's how you would access it. If you'd like to see about renting the telescope or to purchase any of the items that have been donated to us. And the only other major announcement would be in May for our meeting, we will have a swap meet again. So if you would like to bring some equipment that you want to sell, get rid of, pass on to a neighbor, it'll work out the same as last time. The sale will start at 7 and go through 7:45. The meeting will start at 7:45 or as soon as we can get the Zoom to work. Okay? And from that, we should see Woody to introduce our speaker, Father Chris Corbally.
Hi, welcome for joining us here. I'm the vice president of the club, but I'm actually the talent recruiter for the club. And fortunately, my good friend, Father Dr. Christopher Corbally, the Italians say Corbally, but Corbally was born near London and entered the Society of Jesus, the Jesuits, in 1963. He holds degrees in philosophy, physics, astronomy, and theology. After ordination, he obtained a PhD in astronomy at the University of Toronto in 1983. Since then, Father Dr. Chris Corbally has been a research astronomer of the Vatican Observatory and was its vice director for the Vatican research group in Tucson up until 2012. With Dr. Richard Gray, he co-authored the book Stellar Spectral Classification, and the kids I run with refer to it as our Bible.
Go ahead, keep going.
Chris? Okay.
Okay, pretty better
And you should be able to see your pages.
good. You can see myself on the corner there. That's frightening.
Well, we can move that.
But that's fine. It's good.
Okay, do you need to see any of
Nah,
that?
it's all just chat. It's words, you know, the crypt things that you always put on slides so you can remember. But I'll make it up. Great to be with you. So in some ways, astronomy can seem like things made up, but no, we do try. It's science, and that's what makes it so much fun. So let's come and talk about ML. Of course, stands for machine learning, and more in stellar spectral classification. So I'll be able to tell you a little bit about those things. I hope there's not too many experts in machine language, because I'm not. I hope we're having at the Vatican our headquarters, which, as you'd expect, is near Rome. So headquarters just outside Rome. We've had a research base in Tucson associated with the University of Arizona since 1981. Clear skies are keeping us here. But over at Castel Gandolfo, our Rome, and we're having a summer school in June. 25 students from throughout the world are coming. We don't ask their religion, but we do want to know that they're skilled and have a passion for astronomy, and we have a wonderful time. And the topic there is going to be machine language and artificial intelligence, you know, in astronomy. So I'll know an awful lot by the end of that month. So let's go ahead now. What we're going to do this evening is why classify the spectra of stars? Spectra you all know, I can call them rainbows, okay, but there's lots of wonderful detail in the rainbows, as we'll see. How do we classify spectra? Okay, and then a little bit about automatic classification, the historical lines of that, current lines, and kind of where we've got to at the moment with automatic classification. Then, of course, I'll bring up what my colleague, if you noticed him, Richard Gray, on there in collaboration with Richard Gray, my colleague and I produced, which was a way of classifying with a machine spectra. So classification of the Lamoste-Kepler spectra, so some features about that, what Lamoste means, and Kepler, interesting stars, and maybe some conclusions. Okay, so let's launch. Why classify spectra? Well, it's an essential activity of science, is where you start. And it is a start because there comes the deeper analysis after it. But to put things in the correct boxes, whether you are doing on the right-hand side geology and the various kind of rocks, and you can do it on the Earth, of course, and hopefully we'll soon be doing it on the Moon, even more so. So, you know, lunology, would that be? Okay, if it's geology on Earth. Okay. And on the other side, on the left, then we have the plants. I just realize that if I move, no, I don't find a cursor. No, oh, there it is. Yeah, there it is. Find the cursor. So, so there's botany there, and my colleague Richard Gray has recently, in fact, he has taken up bird watching, and is a wonderful expert at that. And I've enjoyed following experts around for a good time. And we classify birds, and you can classify them by their sound, so you know what their sound is, what that sound is, and all kinds of things. The plumage is wonderful there. So the two goals of MK spectral classification. MK stands for Morgan and Kinnan. These are the people in the 20th century who refined this way of classifying stars. The history goes back to the 19th century. So, spectral classification and spectral analysis. Well, to analyze a star begins with estimates for the physical parameter of the stars. And what these are we're just not designed right, are we? Another couple of arms would be ideal. Maybe we just need to go back in evolution and you know, set things right. You can envy insects sometimes, can't you? But millipede, maybe that's a bit too many arms and legs. So metals, or this is the astronomy is very simple. We've got three elements. We've got hydrogen and helium, which come from the Big Bang, and everything else that astronomers call metals. It's so easy. Okay, but that's what the M stands. It's an overall abundance of elements more than other than hydrogen and helium. Now, spectral classification helps us by providing an unbiased determination of interstellar reddening. Oh, there we do. We really have a complication there. Because you may be looking at a star in the galaxy as way out there. If in between that star and us, there are clouds of particularly dust, but gas as well, that will redden the light of the stars. So that can confuse just basic what we call photometry, or the brightness in various colors. And so classification, by knowing what that, you know, how red or how blue that star should be anyway, can give us an idea of whether there is intervening matter between us and it reddening the light of that star. That's important for the analysis. Calibrations of spectral type, as I said, give good first estimates of the surface temperature of the star, of how compact it is, or the surface gravity, and the abundance of elements in it as well. And then the spectral type also serves as ground truth for checking the results of further analysis. So you basically get at your detailed spectrum and, you know, happily go with the analysis. Do the figures you get at the end make sense or not? And your classification of the star can tell you that. So they're good ground check on that. Okay. So the second goal is identification of peculiarities and astrophysically interesting stars. So the odd guys, or gals for that matter as well. So these are interesting. So the spectral classification can identify stars worthy of further analysis. It's worth your putting further work into it. Good, okay. And that the knowledge that the star is peculiar in some ways is vital importance in your spectral analysis. So getting the right numbers at the end as you look at the detailed parameters of the star, its abundances, its temperature, its surface gravity. There are some peculiar stars. Okay, we have funny symbols from AP, peculiar stars in the A-type, AM, okay. And these have metals in them, abundance, which are rather odd, and can also stand for magnetic. The atmospheric structure can deviate strongly in these peculiar stars from standard model atmospheres that you're comparing the spectra against. Okay. So how are spectra classified? Now, let me see if I can find the cursor. There it is. Okay, there's the little cursor. Yeah, because I think this is important. See if I can come around here and get close to, back we go. With the star, the absorption is happening. We're doing there. We're fitting our unknown star into the patterns, of the known stars, the grid of the known stars, the standards top and bottom. So that's what you're doing anyway with classification. You're fitting them into a grid of standards. Automatic classification, yeah, this has been certainly as soon as we get digital spectra like this, so obviously initial spectra started out hand-drawn from the Jesuit Angelo Secchi and others at the telescope, and that hand draw what they saw through the telescope and the prisms that they were using to spread the light out. And so they were drawings of the spectra. Wow. But then came photography, became sensitive enough to get spectra. And then, of course, late 70s, 80s, digital spectra came along. And ever since that time, it's kind of a holy grail to classify these digital spectra. Computers love digits. Surely we can get computers to classify the stars. So various, early techniques, the metric distance technique. So you take those various features that we saw in the spectra and you get a value for how deep those little teeth are, and you compare one with the other. You get values for that. You get values for those teeth in the standards of the Morgan-Kinnan, and you try and then you get the computer to do a least squares. So I guess the computer will make your unknown spectrum, the program spectrum, as close as possible to one of the standards in the grid. Least squares, it's called. Okay, artificial neural networks. So here we're coming into machine learning. Yeah, it's kind of like your brain. Put stuff in and you get stuff out and you hope it's good. How you, as it were, put your stuff into the computer brain is by giving the computer a lot of stars, spectra, that are of a particular Morgan-Kinnan type, MK type. And so if it can recognize that type, your unknown, and say, oh, yeah, it's like this kind of cloud of F6 5 stars, so it's close to that. Yeah, okay. Presumably, but being artificial neural networks, just as you don't know what's going on inside your brain, though obviously a lot more is happening about that to neuroscience nowadays, we don't really know what's happening inside the brain, but it produces an answer. So lovely, like your brain does. Number 3, fuzzy logic, knowledge-based systems. If that seems all fuzzy to you, not surprised. It is. Again, rather like the first, the metric distance, it references the Morgan-Kinnan standards, MK standards, through a list of the strengths of the lines, what we call line ratios, one compared with another, the line strengths, and band fluxes, okay, when your bands are in a moment, bands of the molecules rather than single atoms. So these, because they have to be, certainly the ANN has to be trained, that's number two, they're computationally intensive, and none of them really identifies and classifies peculiar stars, because this cloud of stars that you feed it are the normal MK stars with normal MK classification. So picking out peculiarities is more difficult. Okay, so current lines, again, you know, this is what I showed you, that slide was from certainly around 20 years ago. Lots of advances in machine learning nowadays. So machine learning can be supervised. Are these wonderful names? Support vector machines. Wouldn't you like one of those? How about a random forest? We've got a forest right here in our midst here. Calling him random might be an objection. Artificial neural networks, hey nearest neighbor, decision tree. Aren't they wonderful descriptions? All with various slightly different techniques of supervised, so they're controlling in some way. Unsupervised, you give it a bunch of a cloud of data and let it get onto it. Data exploration by clustering analysis, dimensionality reduction, visualization, outlier detection. Can't you do all these things just off your head? Wonderful. But this is the unsupervised. Just say some are supervised, some you let the machine do it and find it out. Semi-supervised, somewhere in between. And particularly for a small group, you've got we're looking at F-type stars earlier in those spectra. Maybe we can, there's some peculiarity among the F stars you want to pick out. So you give it a limited training set with stars of this peculiarity. So that's the semi-supervised. You're controlling a bit what you're giving the machine learning to get on with. Deep learning, okay, convolutional neural network. Yeah, our brains are pretty convolved. Wonderful names. These are great. So where are we now with automatic spectral classification? Increasing number of methods, and that's always good. We can compare one with the other. The ANN, or artificial neural networks, produces good results, but it's a black box. You don't know what's going on within the brain. Sometimes you'd like to, because there's physics in there. Training stage, it needs a large bunch of spectra whose classification and that adds overhead. They tend to do spectral type only, not luminosity. Spectral type is that horizontal axis of the HR diagram, where we're putting a star spectrum in, giving it a temperature. So from the classification, we know its temperature. The other, the luminosity, or how bright it is the other axis of the HR diagram. And for the moment, automatic spectral classification doesn't do well on luminosity. Well, kind of. Peculiar stars tend not to be classified unless you're targeting these with that sort of the semi-controlled methods, semi-supervised. Deep learning with CNN. Oh, it does get quite accurate. 1.23 of a subclass. Now, we were going from F6, F7 for the middle one, F8, though we're going through subclasses there among the F stars. So that's pretty good to get it kind of within just a bit more than one subclass. So it could, middle one, it might have been machine class through machine learning as F6 or F8, and much of the time it would come out as F7. Not bad. 0.72 of a luminosity class, that's a fair jump, but at least it's quite good. But maybe we can improve. So maybe there's a case for template matching, which is basically what you do when you classify a star by eye, given that grid of standard star spectra that from Morgan Calandis was. So at your telescope, to do it this way, you take spectra of the grid of standard stars that Morgan and Kinnan has set up. So you take a spectra for each, as it were, slot in the whole grid. And then with your unknown star, you try and put it in where does it fit best. And that's what's called the template matching way of doing it. Now, so Richard Gray and I said, wouldn't it be lovely to teach a machine to do what we do? Take that unknown spectra and put it among that grid of Morgan Kinnan standards. Match it the same way that we do by eye. So MK class, which is a program, is an expert system designed to classify spectra in the same way as we humans do, by direct comparison with the grid of MK standards that you've got taken with your telescope. So this maybe 100 or so stars would make a nice grid of these standards. MK class is also designed to detect and classify many of the common peculiarities. There comes the fun, fulfilling the second goal of spectral classification. And you can get it for yourself. So go to the website and it'll come at the end as well. You can do it yourself. There are, we'll see in a moment. Yeah. So programming of MK class, why did we do it? We were approached by an international team. The kind of leader of the team was in Belgium. The telescope was in China. The telescope produced spectra of 4,000 objects at the same time. We initially were confronted with 20,000 spectra to classify, going up to near 100,000 spectra to classify. Richard and I had something else to do with our lives and spent the whole time classifying these things, and hence evolved MK class. It conforms to the basic characteristics of an expert system. There's a knowledge base, that's the grid of standard stars, and there's an inference engine, so it gets to work putting your unknown star within that knowledge base. It requires the use of a specially constructed MK standard spectral library. And currently there are two. With our Vatican telescope on Mount Graham, so down in the southeastern side of Arizona, I've now given Richard 100, the spectra for another library, which is a different resolution, a different coverage than the ones he's got. It's actually more like some of the spectra we were getting from this China telescope, the MAST. So a preprocessor manipulates the program spectra to conform to one of the spectral libraries. Okay, so you've got to prepare your unknown spectrum so it's going to fit in a bit. Okay, but given that, this is how it all works. Simple, isn't it? Well, yeah, so you start on the left and the input spectrum. You then look at it as actually a human classifier do roughly and say, about where does it fit in the whole grid of my standard spectra? And basically, if you do it enough, you've got the grid in your mind. And roughly anyway. So you can fit it into O-type of the very hot stars, going down to the bottom, the KM, the cool stars. And you can either have what's called rectified spectra, which are kind of, they're all, the top of them is all comes up to 1. the value of 1, they go between 0 and 1 for the amount of flux. That's rectified, flux calibrated, another kind. So you can push them into one or the other category and then give them a rough type. So you start putting them into that kind of middle set. You see O type, B type, A type. You can put them into one of those boxes. Now, the arrows between the boxes. So if the machine, MK class, puts it in one, and then after a little iteration finds, no, it's not quite right. It should be not an A type, it should be a B type. It should be a little bit hotter than that. So you can do that. And all the while you're comparing with that column towards the right, the standards, the grid of standards. So all the time you're anchored in the standards. And you can get a final MK type, but then you can always go back and iterate. You can tell them, the program, I want to iterate at least twice and maybe 3 times if your errors of the machines working out are not good enough for you. So you can do that. Also, notice how at the bottom, non-MK peculiar types, we've taught it a certain number of peculiar types, not all, not everything, but at least some, as you will see. So this is it's no longer a black box. It's doing what we do as a human type. And often if you have to iterate, you find it's an A-type standard, say, like an A-type star. Maybe an F, as we've seen, but then, its luminosity is different. It's not a dwarf, it's a higher luminosity, it's a giant or maybe a supergiant, and that will change it a little bit, which of your MK standard it fits best with. So luminosity is going to change and you need to iterate again. MK class does. Okay, just a minor point for the technical minded. Your spectra's got to be good. The problem with this star, which came from the Lowell spectrum, is it seems to have negative brightness. That's no good. So you've got to make sure your data is a good set of data and before that. But now here's a comparison between this expert program, MK class, and human classifiers. And sorry, I have to admit, Richard Gray and I, the human classifiers, we had something over 1,000 spectra from various programs we were running, and we had classified them carefully. We'd fought between us about the classification, doing it by eye, and settled on what was the best classification for the stars. We gave these spectra to MK class, and this is what it did. Human on the left axis going up, MK class on the right. This line is not drawn through that data. It's a one-to-one line. It's and the data fall right on there. So MK class is doing a pretty good thing. With the temperature type, that's what we mean by the B, A, F, G, K, M, as you see on the bottom. Luminosity, it also does a great job, just about as good as sometimes even better than Richard and I, if we don't agree. So it's doing a fantastic job on the luminosity. You can see the standard deviation there, and the top is 0.52 luminosity class. And between a dwarf star and what's called a subgiant, or class 4, is what we mean by a luminosity class. And a subgiant, class 4 to class 3, that's another luminosity class. Okay, for those who are involved with spectra. So examples of interesting stars discovered by MK class in the Lamos telescope, and that's on the left-hand side, and the Kepler spectral database. Kepler was a telescope up in space, and it for a number of years just stared at a patch of the sky in Cygnus the Swan, which if you hold your hand up about that size patches of stars. So along with colleagues, Chinese colleagues, they said, well, let's observe all the stars that are in the Kepler field and get spectra of these, not just the brightness variations, to find out what these stars really are. And so this is a wide field spectrograph telescope, and it takes, as I say, up to 4,000 spectra at a single shot. Wonderful. But that's why you need MK class. So this is what MK class does. And I'm not going to go through the nitty-bitty details because you're not a primary spectroscopy surgeon, and afterwards come. Also, I probably need to go and point out things a bit more than I can at the moment. But what you can see is that there you have a couple of stars that are peculiar. So they're not, let me just move that down for a minute. So the top one, it's a B8 star, so that's a fairly hot star. It's 4 to 5. This is the classification, by the way, that MK class gave it. It's got strong silicon. You can see that silicon 2 line at the top that's pointed out there, but helium is weak. Okay, interesting star. The bottom one, it's a bit cooler, A3. It's a dwarf like our sun. It has strong strontium and strong silicon, and the lines of strontium are pointed out there, and you can see it from the top spectrum where silicon comes. Just by that, actually, a very strong hydrogen line, the big jag, the big tooth. I suppose I can. Yeah, there we go. Big tooth, silicon up there, strontium down there. There we go. Okay, so fine. How about another odd one? Okay. So at the top and at the bottom, we have standard stars. So MK straight standard stars, lovely. In the middle, we have definitely an odd one. Why is it odd? Well, the big teeth, okay, hydrogen. So the absorption produced by hydrogen. The big teeth are like this top one. So that's why we call it an F0. But this sort of fuzz of lines, which is from elements other than hydrogen, is actually much closer to this hotter star A5. Yeah, so that's why we call it F0K, and there's a K line, a thin line between two big teeth there. The K line is like the A5 standard. The metals and the other elements, more than hydrogen and helium, are more like the standard at the bottom. Lambda Boo, now that's an odd one. This is very characteristic of a Lambda Boo when the magnesium line there is weak compared what we'd expect from a standard star. So these standard at the bottom has the elements, you know, the little jags, the little fuzz there, rather about the same strength as the low lines there in the middle one. But magnesium is definitely much weaker than in the bottom standard. Okay, Lambda Boötis stars. We don't know why they're odd. 80 years later, after Morton and Kinnan, in the atlas they produced, said there's an odd star, Lambda Boötis. We don't know where it fits. We still don't know why it fits. We're finding other stars like it. We don't know why it fits. Boötis, if you follow the Big Dipper, if you follow the arm down, sort of the arc of the Big Dipper, it arcs down to the constellation of Arcturus. And that's Boötis, its Latin name. Okay, and it's one of the stars, the Lambda one from Alpha, Beta, Gamma, getting fainter. You can just see it with your eye if you're out in a reasonably dark place. But it's odd, it don't fit, and we don't know why. So that's kind of the fun of stars. What do we have here? Okay. Well, we've got the F5, we've seen that, the standard in there. We've got the F6 above it, just a little bit cooler. And its strontium is strong. You can see the strontium line there. Okay, that's strong. Okay, that's good. How about the bottom one? Well, F4, so it's all the lines, especially the hydrogen, a little bit stronger than the F5, and so it's a little bit hotter. Otherwise, but no, strontium, yes, that's a bit strong as well. But we've also got, what's this CH? That's a molecule, carbon and hydrogen. And so it forms not a tooth, but as it were, a dip, what we call a band. So molecules form bands. And there's something odd about this. Its band there, its G band, is a little bit stronger than usual. So what's happening there? Okay. This is now getting cool stars. At the top, we've got two giant stars. K3 means it's a giant stars. Its atmosphere gets out as far as our Earth is from our sun. It's enormous. Don't get close. Its CN is strong. CN is cyanogen, carbon and nitrogen, and it makes this band or this dip here. It's stronger than in the standard star. So, okay, that's good. So probably an overabundance of carbon or of nitrogen is going to make that. Why? That's where life gets interesting. The bottom, a G85, 4 standard star on the bottom. This one has got strong barium, ionized barium. And as part of the spectroscopy group will know, barium is one of the elements produced in what's called slow neutron capture processes. How did this star, which has only just started going through its later stages of life, get strong barium? You can't ask it, we've got to puzzle it out. Okay, but it's part of the fun. How about some other things? Oh, white dwarfs, end of a star life. A star will become, if it doesn't explode, it will become a white dwarf. So our suns can become a white dwarf. So in the class, we'll pick out some white dwarfs as well. And there's some basic types of white dwarf. We've got the strong teeth there. So it's an A-type, but it's a dwarf A-type. These teeth are quite different from the other ones that I'm showing you in the other spectra. This one is a dwarf A star, but it's got a huge bit of emission there in a hydrogen line. You see there, which is sort of general slope there. DZ is one that's relatively rich in elements heavier than hydrogen and helium, as you can see, compared with the DC, which is above it. So yeah, MK class will pick out some white dwarfs. And the more you teach it, the more you can refine that. And you can have stars that go bump. So this is a dwarf nova, UGEM, we'll put those out. These are our familiar hydrogen lines. Instead of seeing them as downwards teeth, they're upward teeth. Look more dangerous that way. So these are in emission. So these are highly excited, something really active is going on there in the star atmosphere. So great things to find. Okay, I think we've had lots of spectra and filled you it up. We've got the idea really. Where do we stand? Certainly, Richard and I and others have found MK class and found it's a very competent spectral classifier with near human accuracies. How about that? What it can always do is, show us the normal stars and spit out, as it were, the peculiar ones that we can then look at in more detail and refine the best description of peculiarity and kind of thought of what's making the star peculiar. It can capable of detecting astrophysically interesting stars in large data sets. That's the fun. And it can classify stars. This is an estimate, 200 times faster than humans, are found on a very modest Linux box, so computer, that it'll classify a star in 1 second. Now, I can classify a star roughly in about 10 seconds. Oh, it's a such and such. But then I'll take, up to 3 minutes or something, perhaps longer, just making sure and checking it against this grid of MK standards, just to be sure. The computer's done it in a second. How nice. MK class 2 can classify noisy spectra. That's the ones that you don't have much light coming from the star, and so you've got a lot of noise there, and features that really shouldn't be there. Extra wiggles in Father Andy's description. And it does actually, for the very noisy stars, rather better than Richard and I can do. So that's MK class, and a little kind of brush with how to, what to do with your digital spectra now. My suggestion is turn them through MK class and see what comes out. So thank you so much. A couple of
Any questions?
classification errors. There's kind of the thing that errors. In some ways, you don't worry too much. Why? Again, as I said at the beginning, classification is the start. And what you're really doing with classifying is describing the spectrum. So it's almost like a verbal description. If I say a star is an F5, Roman numeral 5, that's actually a description, the best description of the spectrum. And then if there are peculiarities, then I can add in that as part of the description. So basic classification with lengthening. So it doesn't need to be precise. So you don't say it's F5.175, not numeral 5, but numeral 5, no, that wouldn't help you for your general overall. Now, when you do the analysis, then you try and make your numbers more precise. Okay, a great question. Yeah. Important.
I'm just curious, the libraries that we have, is that mostly for our own galaxy, or are you also doing stuff for other galaxies and narrowing them together?
Oh, yeah, so how about other galaxies? Well, this is stars. So yes, there are obviously stars in other galaxies. You don't get as good a resolution, a good a spectrum, but you can classify them roughly, yes. And of course, actually, Bill Morgan, so Kinan, his partner in this, but Bill Morgan started classifying galaxies from their spectra. So he is fascinated by galaxies as well, and particularly fascinated by our own galaxy and the various populations of stars in our own galaxy. So he is an important person in the conference actually that took place in Rome about the populations in our galaxy. Kind of the generations, let's say, of stars. So yeah, you can do it, you can extend it to the spectrum. But again, your precision is going down. There's also the, for the stars in our own galaxy, I've classified little tadpoles of spectra, tiny, not much resolution at all, but enough to say it's about a such and such. And then you can then look, and then I've gone and looked with picked out the objects that were interesting of a certain group, and then looked at them in more detail with a large telescope and a more detailed spectrum. So, yeah. Does that sort of answer your question? Yeah. Okay. Lovely. Good. Any from okay, nobody's chatting. Any more then? Yes.
If you look at Spectral and anything, the James Webb telescope about,
George, no, apart from what, that they're sort of shown initially, those spectra are in the infrared. And so, yes, you can certainly classify stars in the infrared, but for me, the best area to classify stars in the kind of spectra I showed you there, which is sort of blue-green area of the spectrum you're thinking in colors. Why? Because there you have the elements varying the most kind of abruptly. So the strength of those absorption features vary most rapidly as temperature or the luminosity varies. So yeah, one can do it, but I'm not a great aficionado of doing. On the other hand, if you, what suddenly pops into my mind, if you have the very coolest of objects, so the new objects we've been classifying, so extending M. Morgan Kinan's scheme beyond that to cooler objects, so that brown dwarfs is one thing. Yeah, there's so little light in the blue part of the spectrum, you have to classify them in the infrared, at least the near infrared, and you do go great guns with that. So the new classification of those cool objects is being done in the infrared.
the reason why I asked, I saw something on YouTube saying that
I'm not sure that they can hear it. Yeah, they can hear through this.
So I was watching this person on YouTube talking about the spectral of galaxies or looking at
Yep.
Years of the Big Bang,
Yeah.
and they were saying that the person was saying that the spectral is the distribution of stars is similar to what we see in galaxies.
The density. Yeah. So yeah, I may be semi-repeated for those people who could only hear through this computer. So what about the, those galaxies, the spectra of those that James Webb is catching at a very early stage of our universe that seem to be higher density of stars than we would expect for galaxies at that young age? I don't know. I'm not in a. I think everyone's puzzled, but only until tomorrow. A theorist can always find an answer, whether it's the right answer. That's what the observational people need to come and test that answer. So a classic, back to stars, a classic thing is the supernova 1987A that exploded in the southern hemisphere suddenly. In a nearby sort of galaxy, actually, large Magellanic Clouds, a star became visible. It was so bright, it actually was as bright as the galaxy itself. So it was a supernova, as we call them. That star should never have exploded. It was a supergiant, right? So they could go back to original place and find out what star it was. It was a supergiant, that's fine, but it was a blue supergiant. Only red supergiants explode. It took theoreticians a week or less. Oh yeah, they're bound to. A blue, if a blue supergiant is such and such, yes, of course it will explode. So so theory is wonderful and always needed to be tested by observation. So let's see about these, these primitive first generation galaxies. Let's see why they're so dense and what the theory comes up with, and whether we can test what the theory comes up with. That's the important thing, the testing. Good, lovely. Stretches us.
Thank you again, Father Chris. Thank you. Thank you. A couple of last minute things. Just keep in mind, we're open next Saturday for Astronomy Day. And keep it in your own way by maybe having a star party in your neighborhood or something to celebrate Astronomy Day. Next month, remember that there will be a swap meet before the meeting. So get out, I'm sure your spouse will be happy if you clean out your garage a little bit, any of the detritus that you might have. And check with the, on the link on the homepage for the used equipment and the loaner equipment that James talked about. Hopefully this will be a great way for us to move some of the donated equipment sooner because we keep getting more donated equipment and we have a very small storage shed by the observatory. So help us out here, buy some of those things. Anything else that anyone else has? Sorry about all the technical difficulties getting started, but it's a new time. Thank you again. We'll see you next month.